Okay, we're reviewing for the final, and one of the big topics is probability. Probability is always a fraction. In the end, it's always dividing a couple things. It's the things that you want, the favorable outcomes, over the possible outcomes. And basically, it always comes down to that. Now, if you sometimes get a decimal as your answer, and then you don't have to divide it by anything, it's because you're really dividing by 1. So it's always dividing. It's always favorable over possible. It's just that you don't notice it sometimes. All right, here are some of the possible ways that you could solve probabilities. Like, let's say that I said, what's the probability that you get attacked by a polar bear and bitten by a dog on your way home from school? Okay, that would be like one of these, okay, 1 in 10 million or something like that. I don't know how a polar bear gets out around here. Times, and then there's probably a 1 in like 10,000 chance of the dog thing. That's much more likely. But then I basically multiply a couple fractions. That's one way you can solve probabilities, by multiplying fractions. Another way is you could create a tree of all the possible situations. Okay. Another possible way to do probabilities is if you have a tree that is the same number repeated over and over again, then you can use binomial. Binomial is good whenever you have a big tree that's fairly simple, like the numbers aren't changing all the time, like it's 50-50, 50-50, 50-50, or if it's 60-40, 60-40, 60-40, then you can use binomial. Do you remember these? They look like that. Let's say I was doing it for a 3-coin flip. Okay, if I'm going to flip a coin 3 times and I want 2 heads, here's tails, 50-50 chance, and I have 2 heads, and that would mean what here? 1 tail. Those are called binomials. We'll talk more about those later. Then blanks are a good one. Let's say that I have license plates and I have 2 of them are letters at the beginning. Then I have 26 choices and 26 choices. And then times by how many number choices I have. Let's say I have 10 choices of number and 10 choices of number. And then I put it all together. So blanks are a good strategy. Another strategy is doing a big fraction involving P's and C's, like the pizza problems that we did, or even the card questions, like there's 52 cards in the deck, choose 7 cards to be dealt to you, and I want all 4 aces, and out of the 48 other cards, I want 3 of those. These have to add up to 52, and these have to add up to 7. Okay, so there's just kind of a quick overview of all the different kinds of probabilities that you've done. You should be taking notes at this point. Some of you are just kind of staring. You won't remember this when you're studying for the final, which doesn't happen for several days from now. Okay, so I'm going to pause for a second. I'll give you a chance to sketch down the main kinds of probabilities we've done. Okay, I realized I wanted to add one more thing too. Another thing that's kind of under the topic of probability is expected value. And expected values, I gave you a way to remember it, PPAA. All the possibilities get listed. Then you do the probability times the amount, and then you add them all up. Remember that? So just sketch that one down, PPAA, to remind yourself of those. So those are the major methods that we've talked about. Let's talk about some problems now. You have to understand the difference between experimental and theoretical probability. Experimental is where you actually do an experiment. Like I flip a coin 1,000 times. Theoretically, how many times should it come up heads? Out of 1,000? Should be what, 500? And then if I actually do it, and then it comes up to like 570, would that make you pay attention that maybe the coin is like off a little bit? If it's 570 to 430, yeah, I'd be thinking, maybe the coin actually does come up more often, heads or whatever. And if you rig a machine to flip a coin, you can make it, if you always put it on a certain way and with heads up, you can make it flip it so that it will always come up a certain way if you have a machine do it, because it's all about how much force you have in the flip and exactly where the coin is being flipped from, like from the edge versus from the middle. And you can, if you got really good at it, I bet you could affect your ability to flip a certain one. Like if you have heads up and you flip it always with the same amount of strength and the same height above the table, but it'd be hard to control all of those variables. All right, anyway, experimental is where you do an experiment, see what the actual is. And theoretical is what you expect. Theoretically, the oil spill shouldn't have happened, but you know, there were so many safeguards that were supposed to go off, but in the real life, it happened. So, all right, moving on. Independent or dependent? If you are talking about two events and like one's a coin and one's a die, do they think they affect each other at all? Then they're independent. And how about the ones like I have a whole bunch of cards and I draw one out and I get the king of spades and then I have somebody else draw out? What's important about that? Did you replace it or not? Okay. And if I replace the card and then somebody else draws, then the events are independent. But if I keep the card out, then they are what? Dependent. And then all your numbers would change. If it was a tree diagram, you wouldn't have 52 different cards anymore. You'd only have 51, right? And or if I got a king of spades, for instance, then there's one less spade in there than there used to be. So all the numbers change if it's dependent. All right, moving on. Mutually exclusive events are things that are separate completely. When two circles overlap like this, though they are not mutually exclusive, then they make a Venn diagram. And here's a typical Venn diagram question. Let's say we have math versus science, kids that are in math class versus kids that are in science class, and the ones in the middle are in both. In real life, in our school, almost everybody's in both. But in this scenario, looks like there's, you know, 30% of the kids are in math and science. Okay, if I was going to answer these questions, I've got to remind you of a few things like, for instance, P of M means probability of a math student, and the common mistake there is to say 0.4. That's the right answer. 0.7, all right. And if I skip down to probability of math and not science, that's where I'd get what? 0.4. If it's math but not science, then it's just this one. All right. Math and science. Doesn't it seem like you should add a bunch of things together, but you don't? What's the right answer? 0.3. This is math and science, kids. And this is math or science, where you add up all of these. So or means, you know, do you have, there'd be a question like this, do you have math or science? And almost everybody would say yes. All right. Moving on. A bunch of those I don't need. This is an expected value question. It's that PPAA. I'd like you to give this one a shot. I'm going to pause while you try it. I'll list all the possibilities, then the probabilities times the amounts, and then add them all up. Okay, so those are all the possibilities over here. All the probabilities are right here. That's supposed to be 10 out of 15, 4 out of 15, and 1 out of 15. And I'm going to do those times the amounts I get. How much do I get if I pick a $1 bill? A 1. And how much do I get if I did a 5? 5 and a 10. And then I multiply them all together. And this one comes out to 2/3, which is 0.66, actually 0.67. This one comes out to $1.33. This one comes out to $1.33. Grand total, $3.33. Raise your hand if you agree that it's about $3.33. Okay, good. Now, remember, the expected value you should never expect. In other words, all that can happen is 1, 5, or 20. I can't get $3.33, right? So what is this 333 thing? Okay, is there a mistake up there? Oh, it should be a 20. Okay. All right, no big deal. I still got my right answer of $1.33 on that. All right, so point is that this is an average. If we had done it, this experiment like a zillion times and then averaged it all out, I'd get 333 on average. All right, moving on. There's another expected value type problem, that one with the big spinner. Gut feeling, do you think it'd be worth $2 to play that game? Yeah. What if they charged $12? No, somewhere between 2 and 12 would be the fair amount. And you'd list all of the P, the possibilities. Then what's the next P? Probability times the amount, and then you add them, and then it comes out to $8.67, I think. Does that sound about right to you? Okay. That means that if they charge $8.67, then what's your expected value? If they charge $8.67 and you're expecting to get $8.67, then what's your result? 0. You'll get nothing, right? Okay, so if they charge $9.67, or they're more likely to charge $10, then what's your expected value? Negative $1 something, right? Which means you're going to, on average, lose about $1 each time you play. That's how like fundraisers work. So they charge more than its expected value is. All right. And it's more expected value. I don't think we need to do that. I'll do more on the next tape.